Right, in our first part, we're going to look at a simple gray, black and white image and check how to import it and what its main features are. So I open a new script and I'll introduce two functions, one of which we know already, but two that we need to actually open and see an image within the Python kernel. So we both get things from matplotlib. Here's matplotlib.pyplot. And we import imread, read an image. And the same from matplotlib.pyplot, we import our favorite subplots to do the figures. Having imported that, we can access an image using imread. And the way to use it is very similar to what we did when we imported CSV data into a NumPy, into a Pandas data frame. So we just specify the path and the file name completely. So my image is in a folder called fix. And the one that we are going to look at is called Cerebellum. So if I double click on it, by default will open with the default editor to see what it looks like. So it's a grayscale image and it's a picture of the cerebellum from Wikipedia. So we don't need that, but just so we know what we are expecting. So it's in a subfolder called fix. So I used that here and it was with a capital C, just cerebellum. Its format is PNG here. And if we want to display it, for example, within the kernel, then we need to assign it to a variable. So I call that cereb for short, for want of a better name. And if we just do that and see what happens, you can see there's an array created. Cereb, the variable cereb is an array, which means it is already a NumPy array. So very convenient function to import an image. And what we can do to display it is use figax, create our figure environment, and then plot the image using imshow. It's called cereb, right? So semicolon at the end. So if we do that, the image is imported and displayed. So that's very convenient. So imread works. You might notice that suddenly we have green and yellow colors. And that's nothing to do with the original image. That is a property of matplotlib to, by default, assign a color map if you have a color. If you have a matrix displayed, like in this case, the image displayed in color. So it's like a heat map, and it automatically assigns a color map. So we can overcome this by taking the keyword argument to select a color map, which is CMap, and assign it a map that is more appropriate. So in this case, when we have to do with a gray image, we might use a grayscale color map. If you don't know that, if you want to have the inverse, so white and black swapped, you can use the reverse, which is sub R. Many of the color maps have this possibility, so you can just exchange from black to white, from white to black. But as we wanted to go with the original, let's keep it like this. So this is our grayscale image, imported, shown. And of course, now we are interested in the NumPy array underlying what we see here. So what I said is just like a heat map, you take the numbers that are in the array and you assign them colors. So that's how the map is plotted here, or how the data are plotted here. So let's have a look at the numbers. The numbers here are mostly 1. And let's first see how that image is organized. So in terms of numbers, cereb, the data array that contains numbers, it's an array that has 224 rows 440 columns, right? So it's a 224 by 440 image. And you can see rows go vertically and columns horizontally. So this is then how it is displayed. And all of the numbers ones? That would be rather strange, right? Well, not really. We can just have a look at some of those numbers in the middle. Let's just take the same code. You know how to access an array and slice through it. You just assign within square brackets, say, what do we want to use? We want to see an area around 200 maybe and around 100. So rows 100, 200 in columns. So let's do it from 100 to 150 and in columns something around 200, 150 to 200. And if we look at those numbers, these are now not ones, like we saw earlier in the overview of the array, but these numbers are somewhere between 0 and 1. So a grayscale image is nothing but a collection of numbers, in this case, organized between 0 and 1. And the meaning, every number is simply a gray scale. So it quantifies the gray scale from black, which is 0, to 1, which is white, right? 0 to 1, black to white, and somewhere in between. So a value like 0.59 is somewhere in the middle. 0.9 is very much towards white, and something that's much, 0 from black to white is very much towards white. And if it was a very small value, it would indicate a darker area. So what we can do is we can, of course, copy that code from above and display the image again that we had before, but now taking the slice that we have identified here. So instead of the whole image, we're slicing through it and showing those numbers that are here displayed above. And if we do that, we can then nicely see it's a zoom, right? Slicing in the array means a zoom into the figure, and we're somewhere around 150, 200, somewhere around here in that central area. And we see nicely the organization, the lamellar structure of the cerebellum, which the original image was. If we go even larger, 140 to 150, 190, so make a smaller slice. And now you can see the individual grayscales, right? Every square is now an individual grayscale plotted in a heat map in a shade of gray. So black means dark, low value, and white means high value or close to 1. And that's all the magic behind images. It's nothing but a set of grayscales in the case of a black and white image. And so just one thing that I might also add here to have a better view, use the keyword argument fixed size. And if you remember, we used it only once. We need a tuple, and we can assign a horizontal and the vertical size of the figure. So if you do something like 12.8, that will make the figure bigger. Let's have a look at a quantitative feature of that image. So a nice quantitative feature is, like we did with the pandas data frames, to look at the histogram. Right? So we have a large number of values that are meaningful because they represent, in this case, in their order, they represent the organization of the cerebellum. But what is the statistics of those grayscale values? And we can look at it by having a histogram of all those numbers that are in the array. So let's try to do it. Let's just try to plot it directly. I just copy this line from up here, make a figure, and then display a histogram. Remember, that's how we do it. Hist, short for histogram. And we can just put the name of the image and specify a binning. And I don't know, bins, maybe 100 or so. Now, if I execute this code, something strange happens, namely, object has no property bin. So that's my error. The key is bins with a plural S. So now, okay, now it works better. Now there's no error in the code. And when we do that, when we try to execute the code, it takes a long, long time and nothing happens. And if you see in the black window, my code is running. So what is it doing? So actually similar to what we did with histograms in the data frame, by default, what the function is trying to do is to create histograms for each of the columns. But because we have 440 columns, we will now get 440 histograms. And you can see where is it? It's not even showing something. So it takes a long time to calculate this and is actually not what we want. It's not even finished. I don't know if I'm patient enough to wait until this is finished. If not, I will just interrupt the code slightly. Might expect, well, we don't want to see 440 histograms because we're not interested so much in the individual column, but it's done something. So if I go down, so here's the histogram, right? And it's nice, and well, it's not nice. it's a picture showing is basically nonsensical. 440 histograms. What we actually wanted is a histogram of all the values. So what we need to do if we want to have that, we need to somehow bring all the values of that image into one column. So this is now a nice NumPy feature. So there's of course a function for this that you can use. And you use it in this object-oriented programming way with a dot and apply it to that object that is the image called Serep. And the function is called Ravel. So Ravel will take all the columns and put them one after the other in one long column. So then we have one column and we can do the histogram from that. And Ravel goes with open close parentheses, no further argument given. So if we now repeat this and even put a semicolon to suppress the output, then we get an image that's slightly better. So, well, slightly better, it's much quicker. Let's put it like this. The image is still very much, well, not much to see there, right? So we have a histogram. The values we can already see are between 0 and 1. We know that. And what we see is a massive column at or near 1, which is more than 40,000 values in that image, 200 by 400 roughly. And so of those 100,000 values, so about half of those values are already almost close to 1. And what is 1? So go back to the image, right? What is 1? Do you remember what 1 was? Meaning of 1 is white. So 1 is the background. So of course, yeah, we're not very much interested in the histogram of the background. So let's try to take the background away. Well, of course, in the plot, what you can just do, just plot me the histogram without the last part. But there's actually a nicer way. So let's have a look at how we can use the very nice functionality of NumPy arrays and to do something to only see the values that are below 1, but not close to 1. And the way to do this is to make a conditional statement in here. And what we're going to do is we're going to select the values from the original array. So we do that, you remember slicing, right? It's a way you can do something. So we put that in square brackets, but we don't do slicing with from here to there, but we say our condition. So what we want to do is that we want all the values where Serep, that array is smaller than 1. So we do that, we'll modify it in a second, but right, you see what happens? Serif smaller than 1 tells me I want to know what are the values in that array that are smaller than 1 or 1.0. And then whenever this condition is fulfilled, so all the smaller values will be true. When it's not fulfilled, will be false. And if you then select the image on that conditional statement, you will only see those values that are less than 1, the true values, and not see the small values. So let's just do that. And what we can see is that on the vertical scale, the number dropped to 12,000. So we have lost a lot of values, but we still have way too many near 1 values there, 12,000 values that are not exactly 1, but just below 1. So that means it's not, the image is not perfect. The background is not perfectly white, but close to white. And we can, of course, now address this by saying, I don't know, 9.7 or something, make it smaller than 0.97. So take away more values that are close to 1. And suddenly you can see, if we take those away, so that means the background, never mind the background, show me the other values. This is what the histogram looks like. Right, so I'm not going to do any interpretation, but if you want to have a look, so values go from 0 to 0.97 that we chose, and then you can see there's some fine structure here. I think if we increase the binning to 400 in this case, yeah, we can see a little bit resolve the fine structure and at the same time preserving the shape of it. And that's the histogram as it comes out from the overall values of that image that displayed the cerebellum. Okay, and now then you know what else you can do with this image as well. So I'm going to throw this away. I don't need it anymore. That was our introduction, importing and dealing with a grayscale image. Right, so for our next part, let's have a look at the color image. Some nice features that are, it's basically the same as a grayscale image, but just slightly more complex. So let me open a new notebook and let's have a look here at the color image. So what we can do is just copy and paste that code, use the same code as before, use imread and subplots, execute it, and now create my image by importing using imread. I'll import from Fix. Not quite. Not quite there. I seem to be in a different folder. I have changed before when I showed you the image, I changed to that subfolder. So that was an error. So I'll just discard the whole thing. Now I'm going back to this folder here, which is actually what I wanted, and start again importing this. And now we'll be able to get our image. That should be equal imread. And now we'll be able to see Fix and Cerebellum 2. So it's also, you can download it from our webpage. Cerebellum 2 should be the color image. And we use the same code as before. I'll just copy and paste that from the previous thing. And then we get our color image. So this time it's a slice through the cerebellum just for a change. And you can see some colors, and these colors are actually there in the original image. This is nothing that Matplotlib has imposed on the image. So in a color image, you see there's no need to arrange the CMap, the color map. It just automatically shows you the right figures. And that's a feature of this function imshow, right? Imshow recognizes when there is color information and interprets it accordingly. So yeah, so we have this image here, something gray, green, and blue, and then some annotation here, and I'm not going to deal a lot of it with it. So what we remember is ImRead, we directly convert the image into a NumPy array. So let's see if that's true. Yes, that's true. We have a NumPy array called array. A main feature that is now novel, or that seems to be different from before, numbers are not between 0 and 1. Instead of floating point numbers, we now have integers, and the integers range from 0 to 255. So here's a quick thing that I need to tell you. So that's a typical way of putting grayscale or color code into an image. So the intensity of, in this case, a color is put into numbers between 0 and 225. We use integers for that. And we'll see in a short a moment what that means. So let's, before we go into looking at this, let's check our shape. Like for any NumPy array, we can check the shape. Similar to before in that it has rows and columns, 154 rows, 327 columns, but 3 layers of that, right? So you can imagine like it's as if we had 3 images, each of which has the outline 154 times 327 numbers, or if you think in images, pixels. So 3 layers stand for 3 different components. And the components that we use here are, put it like this, RGB. So I don't know if you're familiar with the system here. RGB is our red, green, blue way of composing an image. So 3 layers means we have 1 layer that only tells you the red intensities, second, the green intensities, and the third layer, the blue intensities. And the color image is composed by superimposing the information from all 3 layers and displaying the according color. So if you are not so familiar with RGB or mentally haven't dealt with it before, just Google or find on the internet one of those displays. There are some ways where you can look at it. Just put in RGB animation or sliders or something. Here's with sliders. So if you can see on my screen, there's on the left side is RGB, 3 sliders that adjust the RGB value of a color image according to the individual slices, red, green, and blue. So unsurprisingly, if I put red full up to sort of 100%, then the image becomes red, image here in that square. And you can actually see the number RGB, and the RGB, you can see this would be interpreted as an integer 255 for red, 00 for the 2 others. So 0 means nothing, black, right? Now all 3 zeros just means black, and if I turn 1 up to 255, so it means full red intensity, and that's red image. And similarly, if I bring up green, and it's this aggressive green that we get out of it, this sort of shiny, put that back to 0, and bring up the blue. You can see on the right-hand side how the RGB value increases, and when it's 255, it's a nice full saturated blue. And the reason why I'm recommending using these sliders, because you can also start to understand how RGB mixing works, which may not be intuitive. So I don't know what you would expect from green and blue, but this is what you get in RGB, 255 for both blue and green, gives you this kind of, what is that, the turquoise or whatever color you want to call that. If you take the green away, if you mix the blue with red, then you have this magenta. And what did we not do? Red and green together. That's maybe a bit surprising. mixing red and green gives yellow. Right, so that's how RGB works, and you can then sort of play around and make everything in between and see how every color, every possible color can be mixed from adjusting these components. So if you want something more brown, then maybe something like this. Too much red, yeah, you can have brown colors in some way. That's how you check RGB. Right, okay, coming back to our original thing. So now we understand how the image is composed. And of course, we can also have a look at this specific image. So let's slice through it first to see the actual color, the actual numbers. So if I take the image and I slice it, I don't know where do we slice it, just somewhere where there's something rather than nothing. So maybe around 60 and 150 or 80. So let's put 80 and 150. So 60 to 90 and 130 to 160, something like this. But because we have 3 dimensions to the array, we have to specify the 3rd dimension as well. So let's take red. So what we will see now is for a small window, the intensities of red in that window. Well, you can see it's just numbers, right? And similarly, if you put 1, then you have different numbers, in this case, larger numbers for green in that area, and somewhere similar numbers for blue. So we are now, of course, in the green area here, and you can see already that color might indicate a little bit bluish. So that's why these numbers are much larger than the red values here. Of course, we also want to see that. Now let's have a look at those things. Let's just copy the code from above. Let's do this whole code, copy it, and what's this? Okay, we don't want to see that necessarily. Just get in the image and see, look at the slice. 100 to 150, and yeah, I don't know, 200 to 240. And then remember, we say then red colors will be displayed. So what did I do? Where's my array? It's 154, 307. So I need to make this smaller, 100 and 140. So now we're looking at the slice at the border where blue greenish goes into yellow. And you can see the individual pixels and how the intensities change. And remember, these are only the red components. So it's actually stupid to see them in color, right? So if it's only red components, there's only one color there. Now we have the same thing as before. It's this way of Matplotlib showing us a color map that is there by default. And if we don't want that, CMap equal gray. And this is a proper display now. This is the intensity of the red component in that image with low intensity black and high intensity white. And similarly, we can have a look at the green component and the blue component. There we go. Right? So this is now the way to sort of extract each of the components individually and have a look in what they look like. And if we wanted to see the whole image, now the whole image in sort of grayscale, then we could do all, and 0. Right? If I put all rows, all columns, 0 will be the complete image and just the red components. So that's now a nice overview. You can see where most red components go, with high values being light and green components look like this, and brighter, of course, in the place where green is, and blue components like this. So it's easy to get those components, and then if you understand RGB, then of course you know how that whole thing then composes and brings together the whole image, which is this one. Okay, so now you can go and do histograms and whatever analysis you do. I leave it here just to show you that from importing the color image isn't really much more complicated, but that this 3-layer structure is a common way. I should also mention, maybe you saw it before in the slide, that there's also other conventions compared to RGB that are used in imaging. And sometimes there's 4 layers rather than 3 and so on, but these are just specialties that all are variations on this theme of having a color image composed of individual layers. And we now come to that important topic of masking. Let me copy the functions that we use. And in this webinar, I'm going to use only the imread to import functions. Let me just use the code very similar to what we did before. Image equals imread. And we have an image in our fix subfolder, which is the rows. So let's get this in. It's called rows, code from before. We import the image called image, and then we make a figure with a certain size, and we display it. Okay, so here's our rows. And what it shows is just this picture of a rose. And it has some green leaves around it, and there's a bud here. So this is open, maybe 1, 2, 3 buds, 4 buds visible in addition. And there's some blue color here. That's a plant called periwinkle. If you know it, it's very frequent in the gardens. You see it everywhere. And it's actually a blue that is a little bit wrong. So it's not what it looks like in nature. There's something done by the camera. This shiny blue that you see here in the image. Well, anyway, so that's the image. And why I'm mentioning this, this is an image that I just took in the garden with my camera, right, or a few days ago. So it's just image from the camera. So any of your private images, of course, bring them here, import them with imread, and you want to see them, display them, or change them. That's, of course, all possible. Any of your photos will be, you can do. So one thing that I just wanted to show with this thing here is a little bit missing at the top and at the bottom. It's in the sort of portrait mode. How do you change it to landscape mode? Right, in the camera is easy. There's probably a rotate button somewhere, and you can click and rotate it 90 degrees. How do you do it in a NumPy array? What you want to sort of, you want to change that by 90 degrees. And the answer is transpose. So what we can do is we can use transpose. So let's first get the image and see its shape. So this is the shape. And what would rotating by 90 degrees mean? Well, exchange rows and columns, right? So exchange the first 2 numbers displayed in the rows and the columns, or swap rows and columns and leave the color otherwise the same for the same place. So we can do that. We can transpose the image, make a transformed image from the original image by applying transpose. Transpose with open closed brackets. And then if we do that, we can check what happens if we do it. Just see what comes out of it. So that's the image, but that's not what I want. I want to see the shape of the result. I think that needs to be dot shape. And if I do that, you can see transpose does something. So the swaps around, but in the wrong way. So it brings us the 3 to the beginning and leaves the 2736 in the middle and puts the rows in the last place. So that's nonsensical. That's not what we want. What we want is rows, columns exchanged, but the layers, the 3 layers, stay the same. So how do we do that? Well, transpose takes arguments. You can specify the order in which you want the original dimensions of the array. So if we want to swap rows and columns, we can say 0, 1. So rather than 0, 1, we want it's 1, 0, swap rows and columns, and leave, that's 2, index 2 for the third dimension, leave that the same. So if we do that, now you can see we have swapped rows and columns from 3000 times 2000 to 2000 times 3000, and we have left the third dimension alone. So if I now copy and paste the code from above, so we don't need the shape, we've verified the shape, and we make sure that we now see the transposed image of the transposition. It works quite nicely, and now we have it in landscape mode in a certain size. Right, so that's our rows done. Well, there's actually more that we can do, similar to what we did before. We have learned that already. Rather than showing the whole image, we can also look at the individual layers of the image. And you remember how we did that? All rows or all columns, all rows, comma 0 are the red layers. But remember CMap. CMap was choose a wise color map, which is in this case gray. And if we do that now, we can see the red intensities of that image displayed in grayscale. So red intensity is high where it's white, and the darker it is, the lower the red intensity. And similarly, I just change it, green intensity of this image is displayed like this, obviously now including the leaves, right? You can see leaves are brighter because they are green, and then the blue intensities are like this, very low amounts of blue. But if you like, you can see the periwinkle because they were blue, so they shine now in white somewhere here in the corner. So, and I mention this because already you see how analytically we can see, we sort of filter already mentally. Now we can see the periwinkle rather than the rows. Before we saw the rows nicely in the red intensities. So we can use image handling, image editing to appreciate those features and use it in order to extract things that we are interested in. And in the end, that's what you want to do in data science, right? You have this data frame with lots of numbers, and then you're interested to get out the important things, the one that interest you. Okay, so that's our last topic. Now let's do masking. Let's see how masking achieves just this, getting certain parts of an image sort of isolated or highlighted. Okay, the way how masking works, I'll make a simple example and I refer to the materials for further details. So one thing is we can threshold. Now we want to use thresholds. So we want to use the thresholds to identify the different intensities, to separate, say, high intensities from low intensities. And this is all that we're going to do today. So using thresholding, and we assign a value. The value will be assigned anywhere to make sense. It must be a number between the minimum and the maximum of your image. So if it's a color image like we have here, and the values are integers between 0 and 255 with RGB, then we'll use a number that is an integer, and that lies between 0 and 255. So let's just set an arbitrary threshold at 100, just because that's a nice number. And then what we want to do is we want to create a mask. A mask is like a template that you can put on top of the image and suppress some features and highlight other features. So how do we do that? We use the image, of course, and our image was called image T, if I remember correctly. Did I transpose? Yeah, the transposed image, right? Our landscape image was the transposed. So I'll apply this to the image. Now, where do I apply it? So I use a mask that I apply selectively to one layer. And the layer is going to be, I start with red, just the first layer. And I want it to apply to all columns in the original, rows in this transposed image, columns in the transposed image, and the layer. So if you want to see what the red layer looks like, we go above, change our display, and here's our red layer. So you can see rows is white, values very high, and the rest is near black, so very small, probably smaller than 100, just guessing. So what we can do, we can specify a condition and we say we are interested in all the values that are smaller than the threshold. So we are interested to select everything that is dark, right? Everything that is not the flower, not the rose. And we do that by saying threshold smaller than image at all the column, all the rows smaller than threshold. And that creates our mask. How does it work? If it's smaller, if the condition is true, if it's fulfilled, if a value at a certain point is smaller than the threshold, so if it's dark, it will be true. And if it's larger, it will be false. So that's also, you will get, just have a look what happens. So you will get a mask, which is a Boolean array, same size as that sheet, the gray sheet, and it will contain true whenever it's fulfilled, small values, and it will be false wherever this is not the case. So we get a Boolean array here. Now when we have the Boolean array, that's very nice because we can work with it. And now that's the miracle of using templates. So we can create a new image, which we call masked. The masked image is when we apply the template, the mask, to the image. So let's do that. So what is our image? The image that we're interested in is the red layer that we worked on, and we want to apply the mask to it. So we multiply with mask, make a little bit more visible, make a space in there. Can you see? Now we have created the mask, which is just a layer rows, columns times 0, only one. And then we apply this mask to the, in this case, red layer of the original image. And we create a new image, which is now image plus mask, and we call it image masks. So obviously we want to see that, and I make a slightly more complex figure with this. And let me see, the figure is now different in that we will have 3 sub-figures. So we want to see the original image, we want to see the mask, and we want to see the final result, which is the masked image. So let's compare how they work. So if we create a subplots with 3 columns, so we'll have 3 panels, and then we can show them. The first will be image index 0. And we use imShow, and we want to show the image, but the original was image sub T, so the transposed image. And just as we used it, which was all rows, all columns, and the red layer, what we did above. So you remember what that looked like, and we'll just see it again. And I specify the CMap again as gray, because we're only looking at one layer. Now, if I now want to see the mask, I can use a very similar convention, just using the next panel, which is X index 1. The next panel is X index 1, and then use imShow now on the mask. And we'll have the same color map just for comparison, just to be No, that's not true. Redo. It's not there. Okay, so I have to do it again. So I will just copy and paste it. First one should show the mask, and we want the CMap to be gray. And then we have to close this and see what happens so far. So we have two images displayed, so it's okay. The right one will do it last. So we see the image first thing, which is the red layer that we saw before. Most things are dark, so not much red. And in the flower, the actual rose, the yellow rose, has a lot of red components. And you remember that red is needed to create a yellow. So, and then when we look at the mask, then the mask is now a black and white image, right? It's either 0 or 255. It's either black or white. All the background is white, sort of true. And the rose itself and the buds and a little bit the small buds that were visible there are black because not true, right? Their red intensities are higher than our threshold of 100. And so the mask is shows this shape here. Now we want to see what if that mask is applied to the image on the left. And that's then very similar to, so just copy and paste this code. So our panel number 3, which has index 2, we want to see not the mask, but the image, the masked image. I just repeat it without that comment here. And that's how we get our masked image. Can you even see that? It's not very nice, but I think you can sort of see what happens. So we have the rose here in the original, quite visible in the red layer. We have thresholded it and sort of identified the rose as false. And then when we apply the mask to the image, everything gets black where the rose was, and the rest is unaffected as far as the red is concerned. The red sort of has lost all its intensive values, so equally for the buds that are also there. And so maybe it's a little bit more impressive if we just show the full image. So this is only the red layer, right? So we have now only looked at the red layer, but if we make a new figure and show up and look at the full image, so in show and look at the image masked, the masked image, without specifying anything, and what is left after applying the red filter. So we took the red out, and what is left here is then this gap where the rose was and the bud was, and then the leaf structure somehow still visible, nicely structured, but of course the red component now with different colors. And that's how you can work with masks. So you define your threshold, you create your mask, and then you apply the image to the mask. And in NumPy arrays, this is just brilliant. It's just a multiplication. Where is it? So I urge you to look at this line very carefully. And of course, you can do now many other things with it. Okay. And if you think this image here and this result is a little bit depressing, I agree. Let's do something a little bit nicer, which is, as you will see, quite straightforward. So we have this image that sort of identified the rose and the bud and took it out of the image. So because, of course, now taking it out means I can also show it, right? If I can cut out, if I use scissors to cut it out of the image, then of course I have it isolated, so I can also show it. So let's see how we can use the mask to actually see what is cut out. And to this purpose, I just create a new image. So you see a little bit of the handling, and I make that from image T, from the transposed image, by creating a copy. Call it image new, so we have both at the same time. And now what I do is I apply the mask to image new. I take the new image with the mask, but because the mask has the dimensions of one sheet, only to the first layer. And if I apply to the first layer, the mask is rows times columns, then I can just say what will happen to the place in the, so before I actually do that, what happens in that image to the numbers where the previous condition was true. So where was the previous condition true? Well, everywhere where there's leaves and so on, all the background, it was true. So I can now access that background and say, make that background 0, which means black, right? So I have access to it. I can change those values in one of the sheets of that new copied image here. And very simple, by just copying and pasting, I can do the same with the green layer and the blue layer. The green layer and the blue layer, 0 and 0. So now I have taken all 3 layers of the original image, of the transposed image. I have applied this make it black to the red, green, blue layer. So means, because if all 3 values are the same, it will be just a gray image. And if it's 0, this is the extreme value of a gray image, which is black. So what do you think? What do you think the figure looks now? I have my original, take my original, applied the mask, but in a way such that the background has been set to 0. So let's do that manually. Subplots with fixed size, same fixed size equal, and the tuple was 12 times 8. So now we have our coordinate system, and we'll do an im_show to see the image new. And if we apply, I don't know if you can imagine it, here is the result of that. That now leaves the rows and the buds isolated. If you think black is depressing, you can also make it gray. I don't know what level of gray you like, but if all 3 numbers are the same, then maybe specifying it 100, it makes a lighter gray background. And now you know how to adjust the value that you want to have. So this is sort of our final image. Now we have seen how understanding the structure of the array and then using conditional statements to create masks can be used very creatively to select certain features and suppress others, sort of to isolate and to identify things in that image. Brings us to the end, and the application of all of this is, of course, when we come to unsupervised machine learning, then we'll do very similar masking in order to find out, for example, to identify brain tumors. Right, thank you for watching. I'll put the video of this recording up on the webpage. You remember that you can download these images, but of course you don't need to. Just take any image from the web that you can find. Take your own photograph from your own garden or journey or whatever you did, import it and have a look at it, have a go creating masks and working with them and see how individual features can be enhanced or suppressed. Take care and good working.